Now for Coulomb's law in all of its vector glory. No more magnitudes. So let's look at the real Coulomb's law. So we'll still have our two charges on an axis. Q1 and Q2 are the charges. And we're now going to call this 1, 2, R1, 2. Okay, so R12 is the displacement between charge 1 and charge 2. The displacement if you go from 1 to 2. So the actual force that we want to calculate with Coulomb's law is F12. So F12, let's be clear what that means. F12 is the force Q1 applies to Q2. Okay? So F12 is experienced by Q2. It's applied by Q1. If you're going to draw it, you would draw it over here. F12, the force 1 applies to 2. It's equal to Coulomb's constant, Ke, just like before. The charges go up in the top, just like before, Q1 times 2Q times Q2. The separation goes in the bottom, R1, 2 squared. So that's the same magnitude as before. We just have some extra notation to keep in mind who is applying force to whom. And then finally, we need the vector part. We need this to be a vector, and you do that with this thing, R hat 1, 2. Okay. So we have many kinds of hats here. We have vector symbols, we have nothing, and now we have this, R hat 1, 2. And this is a unit vector along the Q1, Q2 axis. Okay? It's a unit vector. It points from 1 to 2. And its magnitude is equal to 1. So this notation is also important for the unit vector because it tells you which way does the unit vector go. Well, if it's labeled R hat 1, 2, it points that way. Okay? And its magnitude is 1. What it does is it gives this a direction without changing the magnitude. Right? That's what this thing does. So you'll see these a lot in your physics book, and you'll see all it's doing is reminding you it's a vector. We have to say which way it goes. Okay? So let's look and see if this works, if this reproduces the repulsive attractive thing. So let's imagine that both charges were positive. Okay? So this one's positive, and this one is positive. Then if we look here, positive, 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 the separation is always, the displacement is always positive, you square it, everything's positive. Well, the force would be what direction? R hat 1, 2. So the force 1 applies to 2 is in the direction that points from 1 to 2. So R hat 1 to 2 looks like that. So for that charge, it did work out. When they're both positive, you get a force that's pushing away. But what about this one? Well, this one, the force would be F21. You switch everything. The force this one experiences, the force 2 applies to this one, is this way. F21. F21. And you plug in all the numbers, positive, everything's positive, but then the unit vector would also be R hat 21. Right? So also the unit vector is in the right way. And here, if I were to draw F, it'd be F12. So the way we're defining this unit vector, that it's along the axis, it points from the first number to the second number, makes the repulsive aspect work out. If one were positive, again, and say one were negative, well, you can see what would happen. The magnitude would be negative. It would point in the opposite direction as the unit vector. So 1, 2, the unit vector is still that way. The unit vector doesn't care about the charges. It's just to find by the geometry. But then F12 would be the opposite direction because of the negative magnitude. And here would be the same thing. The unit vector 2, 1 is still that way, but then the force would be this way if they were opposite charges. So you can see the way we're defining the unit vector does reproduce the attractive and repulsive for opposite and like charges. So unit vectors are important. They really do help you see which way a vector points, and we're going to play with them quite a bit more as we move along. We're going to now work a problem that requires the vector form of Coulomb's law to calculate a force. And of course, the vector becomes useful when you go to 2 dimensions. We've done enough one-dimensional problems where you can really just look at the magnitude. Now we need to do a 2-dimensional vector problem. So this is one from the book. 4 identical charged particles with 10 microcoulombs of charge are located on the corners of a rectangle with length 60 centimeters and width 15 centimeters. So calculate the magnitude and direction of the force on the charge in the lower left corner. Okay, so to start any problem like this in physics, you need a coordinate system. You always start with a coordinate system. So we are going to do this in Cartesian coordinates because they're a rectangle, so that kind of makes sense to go with standard Cartesian coordinates. Let's see, it said they were on a rectangle 60 centimeters wide and 15 high. So here's one of the charges. Let's go ahead and put one at the origin. That makes sense. And put another one here. And then that can be the 60. I'm going to put 0.6 meters down there. And then the other part of the rectangle was shorter. And this isn't quite to scale, but I'm going to call that 0.15 meters. It's not even close to scale. So there's your rectangle. And there's your 4 charges. The next important thing to do in these problems is to label those charges. Even if the problem didn't label them, you need to label them to keep up with all those forces. So I went with 1, 2, 3, and 4. And in this problem, one nice thing is that the charges are all equal. All equal to 10 microcoulombs. 10 times 10 to the minus 6 coulombs. So that's the first thing you need to do to set it up. And then they ask for the force on the lower left charge, which is the one we put at the origin. So now we need yet another notation. We're going to write a bunch of these F 3 to 1, 2 to 1, 4 to 1, but we need just the total force on charge 1. I'm just going to call that F1. Okay. We're calculating what is the total force on charge 1. And we're going to use that fancy word superposition. So the way electrostatic forces add in this situation is they add. You just sum them. So it's superposition. So what we say then is the total force is the force that 2 applies to 1, F21, plus the force that 3 applies to 1, plus the force that 4 applies to 1. You just add them up. So now we just need to get each one. Let's do 2, 1. And let me put one note. I'm going to do this all MKS units. So I'm not going to write the unit in all the little expressions. I'm just going to, everything is MKS. So I'm not going to write meters and coulombs and newtons and all that. Okay, so F21 equals KE 9 times 10 to the 9 times the charge. And it's actually the same charge, so I'm going to write it squared. So it equals 10, what was it? 10, yeah, 10 times 10 to the minus 6 coulombs squared. Right, but I'm not writing coulombs. Over the separation. So 2, 1 was 0.15 meters squared. Okay. And then we would write r hat 2, 1. And we would see what we get. You plug in all those numbers, you get minus 40 for all these numbers. Or you get 40, I'm sorry, 40. And now we have to think about the direction. And this is an aspect of the problem, sometimes you call it inspection. Which way is r hat 2, 1? Well, you just look at it. 2 to 1, so it's a unit vector along this axis. It points from 2 to 1. There's r hat 2, 1. It points down. If it points down on the y-axis, then the way we would write this in Cartesian coordinates is the unit vector for the y-axis is j hat, but it's down, so it's negative j hat. So just by looking at which way the force goes, we stick that negative there. Minus 40 j hat. So it's a little bit of inspection, just looking at it and thinking about which way everything points. We can also do, very similar, is F41 equals 9 times 10 to the 9 times 10 times 10 to the minus 6. That's 10 microcoulombs squared. Over the separation for this one is 0.6, 4 to 1, 0.6 meters squared. And it's r hat 41. So if you work all that out, you get 2.5 is the magnitude. 2.5 newtons. I'm just not writing it that way. And this one, its unit vector 41 looks like that. R hat 41. Magnitude of 1 pointing that way. So this one is on the x-axis, so that's the I hat direction. And it's negative again, because again, the force is going in the negative direction of the axis. We assumed x was positive this way and y was positive that way. There you go. All right. So again, we're just kind of looking at it and using inspection to decide which way it points. Finally, there's F31. 9 times 10 to the 9, 10 times 10 to the minus 6, quantity squared, over, this distance here. Let's see. So we can get that from the Pythagorean theorem. It's a square root of 0.6 squared plus 0.15 squared. Square root of 0.6 squared plus 0.15 squared. But it's a square root and then it's squared, so I'm just going to leave it alone. I'm not going to jerk it around and square root it and then square it because I'm running out of room. Okay. But this is 0.6 squared plus 0.15 squared in the bottom. And it's r hat 31. All right, so the magnitude of that one is 2.35 newtons. But then, what is the direction? You look at it, I can draw the unit vector, 31, it's like that, r hat 31, but it's not something we can yet put on a Cartesian axis. It's not along a Cartesian axis. So we have a little bit more work to do. So let's think about this direction a little bit more. I'm going to redraw this just to make it a little less junk on it. Let's see, this was x, this was y, and our problem is between 3 and 1, we have a unit vector like that. That's the direction of our force, r hat 3 to 1, and we need to know that direction because we need to break it into x and y coordinates. This one does not just naturally lie on an axis. So it's hard to see the direction here, but you can actually see it's up here. You can see it in here because here is the direction. And this is on a right triangle that we know everything about. Okay? So we know this side of this right triangle is 0.6, and we know this side is 0.15. So since we know those two things, we do know that angle. So you got to think back to your SOHCAHTOA. I don't know if they still... SOHCAHTOA is a word we learned to help us do trig, at least when I was young. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So we know that the tangent of theta is 0.15 over 0.6. So if you throw that in your calculator, theta is about 14 degrees. Okay. So that theta is the same as that theta. This is still the x-axis. So now we can break it in components, and you can see that it's going to have a negative y component and a negative x component. Let's see. So we could then write this F31. So starting with what we had before, F31 would be the magnitude 2.35 times these sine and cosine components, but it's also negative. Just by inspection, just by looking at it, we can tell this axis has a negative component, this axis has a negative component. So we're going to put in the negatives, minus 2.35, and remember it's newtons, I'm not writing the units, times the cosine of 14 degrees. That is the I hat. That's the x-axis, because the cosine is the adjacent component. And then also minus 2.35 times the sine, in this case, of 14 degrees, and that's the y component. Also negative, because this is pointing towards negative x and negative y. So if you put those together, you get minus 2.28 newtons I hat minus 0.57. Oops, I wasn't writing that. Minus 0.57 newtons j hat. So there, we've broken the F31 into the two Cartesian components on the two Cartesian axes. So now you do the entire sum. So you say F1, and you just go through and you add up the I hat part of each of those vectors, and I'll give you the numbers. The answer is minus 4.78 I hat. And then you add up all the j hat numbers, the minus 0.57 and the minus 40, and you get minus 40.57 j hat. And the whole thing is, of course, newtons. So that's the final force on charge 1. So you may have noticed when we did this problem, there were several points where we had to think about it, just which way do things point? And we had to sort of arbitrarily say, oh, well, it's in the negative x direction or the negative y direction. So sometimes you want a way where you don't have to do that. If that really bothers you, I'm going to show you another way to do this problem. However, it's a little bit risky because it may completely destroy your understanding of electrostatics. You may never recover from this. Okay? So if you're really happy with how we did it in Unit 5, just turn it off. Don't watch. You don't want to see this. Okay? If Unit 5 was just completely enjoyable to you, then stop. But if it bothered you when we said, well, it's negative, then watch this at your own risk. Okay? To do it this way, we're going to try to do it without all that inspection, all that thinking about which way things point. And to do it, you really have to be really good with unit vectors. So let's look at our unit vector again. For example, let's do r hat 1, 2. So when we looked, well, or we called it 2, 1. Okay, let's do 2, 1. R hat 2. When we looked at it, we had to just think about which way does r hat 2, 1 go. But we can also go with a mathematical definition of r hat 2, 1. Because what was r hat 2, 1? It's a vector in the direction along this axis. It has a magnitude of 1. So let's think, how would we make that? Well, we need yet another vector. We need the vector r 2, 1. The vector hat 2, 1. The vector 2, 1 is literally just, I start my chalk at 2, and I go to 1, and I put an arrowhead on it. It's the vector from 2 to 1. Okay? So that's pretty straightforward. There's no guesswork there. Positive, negative, you don't think about that. You just put your pen on 2, draw it to 1. That's vector 2, 1. That will be guaranteed to be in the direction on the axis from 2 to 1. Now we just need its magnitude to be correct. So what do we divide? Well, we divide by its length, by the displacement, r 2, 1. So that's actually a mathematical way to get that unit vector, rather than just looking at it and thinking, well, negative y. Okay? You might see in some books, they might write it like this. Since this is a magnitude, they might do it like that. Go ahead and call it the vector r 2, 1 and put the bars around it. Or what we've been kind of doing is when we see nothing on here, when it's just empty on top, we know that's a magnitude. That's the displacement in this case. Okay? So now, here's the scary part. Now we're going to write Coulomb's law again for the case 2 to 1. It's going to be Ke. It's still going to be Q2, Q1 But now it's going to be over r21 cubed times r21, r vector 21. See? So before we had r hat 21 sitting here. So now if I bring that here, that puts another r21 in the bottom, and now it's cubed, but I have an r vector 21 there. Okay? So when I write it this way, is it different? Is it some different Coulomb's law? Is it a Coulomb's law that goes as 1 over r cubed? No. It still goes as 1 over r squared. We have an r cubed down here, but now we have an r in the top. Okay? And when you cancel those out, it's still going as 1 over r squared. It's the same Coulomb's law. It's just a way to write it where we don't have to guess what r hat 21 is. Okay? So let's use it a few times, and let's see if it actually does anything for us. Okay? So let's write F21 is 9 times 10 to the 9. Again, this is all MKS units, times 10 times 10 to the minus 6 squared over the separation cubed, which is 0.15 cubed. And now we just write the vector r21. Well, it's 0.15 and it's pointing down, so it's negative 0.15 in the it's I hat direction. If you multiply that out, you get minus 0.15, I'm sorry, j hat direction, you get minus, if you multiply that out, you get minus 40 j hat. Sorry. And then we could also do F41. And it's the same thing, 9 times 10 to the 9 over 0.6 cubed times, on the top we have 10 times 10 to the minus 6 squared. And then we just write the vector R41. Well, that's minus 0.6 because it's this way, I hat direction. Minus 0.6 minus 0.6 I hat. And that'll give you the same answer for that component, minus 2.5 in the I hat. And now I can tell you're massively unimpressed. It's the same thing. All I'm doing is cubing it here and then putting one up here, and they cancel. And I still had to kind of look at it to figure out which way our vector was. So really, is this any better? Okay, let's do one more part. Let's do F31. That was the difficult one anyway. Right? Let's see, F31. That would be KE 9 times 10 to the 9, 10 times 10 to the minus 6 squared over the separation. So remember the separation, it was the square root of 0.6 squared plus 0.15 squared. Before I didn't even bother with the squares and the square roots. I just wrote it down that way. But now it's not squared, it's cubed. Okay, so now to write this correctly, it's 0.6 squared plus 0.15 squared, and it's to the 3 halves. Right? It's a square root of that to the 1/2, but it's also cubed, so it's to the 3. So you multiply those, it's to the 3 halves in the bottom. And now, we don't write the unit vector, we just literally write R31 as a vector. Well, we look at our diagram, and you remember it was minus 0.6 I hat and minus 0.15 j hat. And that's it. That is your vector. If you break that down into components, solve everything, do this 0.6 squared plus 0.15 squared to the 3 halves, you'll get minus 2.28 I hat and minus 0.57 j hat. It gives the same thing we got last time. And then when you go add them up, F21, F41, F31, of course, you still get the same thing. So you see, we got the same answer with this formula, but we never did any trig. How did we do it without trig? Well, you don't always need trig. Trig is really, in this case, in a lot of cases, just a way to do ratios. There's other ways to get to ratio something out rather than having to use a tangent function or an inverse tangent to get theta. So it's really the same thing. It's just a way to do it without really having to think about the trig and the angle and the 14 degrees. We never put that in. All we had to be able to do was write the vectors r, r21, r31, and r41. So this is just another way to do it, but the most important thing to realize is this formula for Coulomb's law still goes as 1 over r squared. Okay, we have a cubed here, we have an r magnitude there. That's the main thing to keep in mind. But this can save you a lot of trouble in some problems.